thank you for the introduction and good afternoon, everybody. And thank you for giving me the opportunity to present this review on high angular observations of protoplanetary disk. I will not be able to present all the exciting science that has been obtained so far, but I will select only a few striking results, and many others will be and have been already presented during this conference. And I mentioned the corresponding talks at the top right corner of my slide. So I will give a few words of introduction, even if we have already nice introduction this morning. So confirmed planetary systems exhibit a wide diversity in orbit, mass, nature, atmosphere, and so on, with super Jupiters separated by tens to hundreds of AU to compact super systems separated by a few AU. And in particular, the Kepler population, as depicted here in this graph, reveal planets with size as small as and orbits as large as those of the Earth. And the origin of this large diversity is still unknown. And to constrain favorable conditions for planet formation, we need to know where, when, and how planets form. So, protoplanetary disks, as said this morning, play a crucial role as they are the reservoir from which matter is accreted onto the star and planets are built. And they are mostly constituted of helium and hydrogen gas with a small fraction of their content in the grains. And as they set the initial conditions for planet formation, the observed diversity of exoplanets might well be related to the diversity of the disk physical properties, and the interaction of the planets with their host disks might also be key, as the massive planets that form first can dramatically affect the disk structures and influence the subsequent formation of lower mass planets. And even if these interactions are brief, they are foundational, since the mutual influence sets some stellar and protoplanetary properties that persist for billions of years. And planet formation and disk evolution processes occur simultaneously, influence one another, and jointly shape the disk structure. And so to understand the diverse outcomes of planet formation, it is crucial to observe the structure and also the evolution of the protoplanetary disks while planet formation is happening. And so our motivation is to have a global view of the protoplanetary disk structures. So starting from the outer disk that is depicted here with the gas in gray and the dust in color. And these gas and dust rich regions are optically thick in the optical and in the near infrared, and the scattered light image has thus sensitive to the disk surface, as it has been well explained and illustrated this morning. And they are directly related to the stellar irradiation, the inhomogeneities of the surface, and obviously to the amount of scattering dust grains. And the micron-sized dust grains suspended in the gas are sensitive also to the radial variation of the dust distribution. Dust in the disk emits also a thermal continuum that span 4 decades in wavelengths from 1 micron to 1 centimeter. And the HALMA images will be in the millimetric range, will trace the pebble-sized particles and the dust density. And since most of that emission is optically thick, these images are more temperature diagnostic. And of course, as also illustrated this morning, gas can be traced through emission line. And this near-infrared and millimetric imaging can be done with an angular resolution of a few AU. So the sample of image disk was significantly increased with the advance of sphere in GPI, in red here in this plot, and this can be seen also in the inset diagram. This allowed to expand the sample towards the younger stars, one with an age of 1 or 2 megayear, and also to lower mass down to 0.3 solar masses. From these large surveys, we can obtain a beautiful gallery of polarized images, and we see some of them already this morning. In gray here, you have the coronagraph masking the central star, and the white bar correspond to a scale of 50 AU. And what we clearly see here is the diversity of the size, of the shape, of the outer disk. And as previously said, this observation traces the upper layers of the dusty disk, where dust is well coupled to the gas. And the morphological substructure that we see here, the rings and the spirals, the arcs, and the shadows are ubiquitous across the spectral type that is mentioned at the bottom of the slide. And the origin of this substructure in the disk is related to the motion of dust particles bounded to the gas and due to drag forces. And this is also related to mechanisms that can produce long-term pressure variations. And as already discussed, this substructure are thus believed to be the result of disk evolution processes, and in particular of disk-planet interactions. And then I refer to the talk, the invited talk on the planet formation theory for more information on that process. So looking at the millimetric range with HALMA, we also observed a wide diversity of substructure in shape here and also in contrast. And we observed cavities and gaps and rings, and again, arcs and spirals. And again, they may probe disk evolution and side post of planets. What is interesting is to compare the near-infrared and the millimetric image, and so as to put some constraints on the dust properties. For instance, when we have a look to the left, the comparisons between the two images with HALMA and SPHERE for TW Hydra, hold both images at the same scale, and we clearly see that we have a difference in spatial extent that can be interpreted as dust radial drift, and the position, the difference in gap position, width, and depth allow also to see some phenomena that trap differently the small and the large grain. Another comparisons in the middle here between the large extended outer disk coming from the sphere image in color, and that can be compared with the HALMA contours in white in the middle, and that is very compact and traces the midplane. And finally, another interesting study is related to the shadow variability observed, for instance, on these Herbig stars, and that is related to the disk geometry and its temporal variation, since marked change in the scattered emission on months or year time scale can be caused by shadowing from the inner disk with its shorter dynamic scales. And that's why it's really important to zoom in. And this is how the way to complement our global view of the protoplanetary disk structure is to zoom in and to see behind the coronagraph in the innermost regions here, and to probe the inner rim where the dust is sublimated, where dust traps or vortices can occur, and also where micron-sized dust grain grow to pebbles and larger bodies, producing the first building blocks of planets. In addition to that, in these innermost regions, mass accretion and ejections through jet and winds, star disk interactions, accretion shocks also occur and impact the evolution of the central star and its disk, and thus, again, define the initial and environmental conditions for planet formation. So for typical distance of star-forming regions, resolving such a scale requires optical long baseline interferometry to reach an angular resolution of a fraction of a U with the VLTI or the chiral ray, and also to use spectroastrometry, for instance, with gravity, to have access to interferometric quantities in emission line like bracket gamma line or CO band heads. And these techniques could be coupled with photometry to follow variability and spectropolarimetric observations to map the magnetic field of the central star. So, since a few years, large programs on young stellar objects have been led in optical long baseline interferometry, and this has allowed to extend the radius luminosity relation in the mid-infrared here with the MIDI atlas, and that will be updated by the MATIS survey also, and also in the near infrared, for instance, with gravity on the right. So you have the Air big star in blue, the T-Tauri star in black, and the massive YSO in pink. And the correlation between the location of the infrared emission on y-axis and the strength of the radial field of the central star on the x-axis show that in this spectral range, the emission is dominated by the dust located close to the dust sublimation radius, whose position itself is primarily constrained by the luminosity of the central star. And what is really important, and what is an important step now, is that we have in hand homogeneous samples in terms of data sets, observations, and modeling. And from that, we can look for trends with the properties of the central star and the disk morphology, flat and flare, with and without gaps, as mentioned also this morning. So here is an illustration of the comparison of the size for F big star in N band in Y and in K band in X, for flare disk in blue and flat disk in red. And this size increased proportionally, and at the small scale level, there is no strong segregation between the two groups of disks, and there is an overlap as found by Mascamp previously. But at a larger scale, we see that the flaring disk appear more clearly in the upper part of the plots. We also look to the size ratio in N to K band, respectively, as a function of the mass and as a proxy of disk evolution. And looking at stars of similar masses, for instance, at two solar massive in the green zone here, we observed for our sample that we have an increase of the N to K size here for the gap sources that are also the oldest one. So here, as mentioned also this morning, there is a great interest of populating such a diagram and looking for a universal scenario, and the advent of MATIS and then of Gravity Plus will help to do that. Such large samples are also key to better understand the connection between the inner and the outer disk by comparing the inclination and position angles of the inner disk with gravity, for instance, and with those obtained with HALMA. And there is a survey of 20 transitional disks led by Bon et al. And here come the results. The analysis is consistent with the presence of misalignment in at least 6 out of the 20 disks of the sample, while 5 disks appear to have an inner and an outer disk that is well aligned. And from this misalignment measurement, using the method from Muro Arena et al., we can predict the position of the shadows in the outer disk. And this is what is plotted here on the right in blue and orange, in the position of the shadow that is predicted and that could be compared with the sphere images, and the agreement is remarkable here. Ideally, what we would like is to make multi-scale imaging of this protoplanetary disk. I will not come back on this beautiful result presented this morning, just to emphasize the exquisite angular resolution obtained with the Char array with an accuracy, resolution of a fraction of a U. And I will give another example on the multiple system JW array. And with here the image of the sphere and the HALMA, large-scale images that show an extreme warp and disk misalignment, and for which optical interferometry allow to zoom in and to determine the 3D orbits and masses of the different components of the multiple system at the core of this object. Unfortunately, imaging the inner disks is quite challenging, at least for two reasons. First, the disks are very compact, and here you have an example of the Herbig survey led by Jacques Kluska. And for the Titori, the disk will be much compact. So you see that the scale is quite small. And secondly, as previously said, also these regions are quite variable. And at short time scale, which implies that to do images, we need to do snapshot imaging. And that's why within this context, the 6 telescope beam combiners of the Char array are really powerful to produce such images. And we mentioned next talk that will be probably that in which we will probably see a very nice images. Another interesting approach is, of course, to combine Pioneer, gravity, Matisse observations, and to have multi-wavelength observations, either through imaging, as in this case for the Herbig star HD 45677, with the image in H band with Pioneer and the images in L band and N band with Matisse. But we can also have this multi-wavelength approach with a model fitting. So indeed, as for the outer disk, comparing the observations in different spectral bands allow to constrain also the dust. So for instance, here in this example, a recent study led by the Matisse group allow to demonstrate the existence of two different dust populations, an inner nanograms in the innermost regions that dominate the near and the mid-infrared emissions in a hot regions, and another dust population with probably larger grain that dominate the emission outward. And the fact that we observe this nanograin close to the star requires a replenishment process. Another example here is the well-known Herbig star HD 163296, observed with all the optical long baseline instrument and recently with Matisse and gravity. And these observations bring new constraint on the dust with hints of vortex-like structure here, and also temporal variability on short time scale. Such a variability also push for simultaneous observations through multi-technique campaign, and that's what has been done on DOAR 44, a solar-like young star with a transitional disk, a compact inner disk, accreting onto the central star, and several hours of observations across the bracket gamma line have been recorded by Bouvier et al. With gravity. So here you have the spectrum of the bracket gamma line, the differential visibility, and the differential phase across the line. And thanks to spectroastrometry in bracket gamma line, the magnetosphere is probed at a scale of a few stellar radii, and a slight offset across the line with respect to the star is detected. In addition to the gravity observations, simultaneous photometry to have access to the variability and visible spectropolarimetric data with Espadon have been recorded. And this gives access to the topology of the magnetic field from which we can derive the size of the magnetosphere. And this is in great agreement with the gravity measurement. And all these observations are fully compatible with the magnetospheric accretion scenario. Similar findings have been obtained on TW Hydra by gravity collaboration, and there is also a talk on another set of Titori stars. Okay, I will finish with the famous case of PDS-17, whose planets have been directly imaged, as seen on the top of this slide. So here on the left, you have the sphere image in color. You have the H-alpha contours in blue obtained with the MUSE instrument. And on the right, you have the HALMA image, so with the planets B and C. And since this, the position of the planets are known, this object has been observed with gravity within the exogravity program. And the orbits of these two objects has been accurately determined with gravity. And a first K-band spectrum at a resolution of a few hundreds has been obtained, and there will be a talk later in the week on these beautiful results. So I will finish with some takeaway message, but some of them have been already said this morning, but I think it's really important that to emphasize that now we have a large survey of protoplanetary disks that has been performed, and a lot of them with a large sample of objects, which allow to do some demographic studies and some to look for trends with the central star properties, with the disk properties, and also this allow to have to study this variability and to follow the variability of this complex environment. And so to address the open questions on planet formation that has already been set, and I'll just write them again here, there is a very strong interest of multi-technique and multi-wavelength campaigns to probe the different scales, the innermost regions and the outer scales, to probe different ingredients and to study all the complex and variable processes that are in play and in interplay in this environment. So I thank you, and will be very pleased to answer your question.
Yeah, thank you very much for a nice overview talk. Is there any questions, either online or in the room? Yeah, if you're online, you can type in chat or raise your hand. We should see it. Yeah, in the meantime, I maybe had one very quick question. On slide 18, you showed some nice images of 163,296, I think. Do we have any idea what is causing the asymmetries that we see, and what will cause the temporal variability that we see in this object?
I'm sorry, I don't hear you very well. So
do we have any idea what's causing the asymmetries that we see in this object, and what's causing the temporal variability?
Probably we will have also a detailed talk on this object. So the question of this vortex here, or this arcs here, can trace some inhomogeneities in the disk. We can have also some change in the dust density or illumination. So what is not necessarily very clear is we have only a few epochs, and we have no simultaneous observation. So we need probably to have a more focused campaign combining all the instrument that we can have and to better understand this object, because the variability doesn't help also to model the things if we used different data sets that are not homogeneous and not simultaneous. But yes, there are some simulations of vortex and of dust trap and dead zone in this innermost part of the dusty disk that has been done in the Matisse people.
Thank you. Is there any other questions? If not, we can thank Karine again. Great talk.